What the heck?
Hectogon.
Hello. So this is going to be sort of a strange video, in the sense that it's not going to be current. I'm not going to film a video. I actually have a video of myself teaching a lesson on exponents and logarithms in a calculus context, sort of with the assumption that you understand derivatives and limits, sort of going through their properties and taking their derivatives and seeing what that is. It's a little more than a half an hour long. It's from when I was going from my sophomore to my junior year of college, and me and my friend who films the video were trying to become teachers. He was trying to become a history teacher, I was trying to become a mathematics teacher. We both realized that's not really what we want to do. When him and I start doing streaming on Twitch, which I will link you to, you'll get to meet that person. His name is Bill. He's my best friend. We roomed together in college for a couple years, so we each had to film the other person doing a lesson, and so I chose to do mine on exponents and logarithms. It's a bit long. It's unedited. I'm just going to post it. So I'll include timestamps as well, so that you can jump to whichever part you need if it gets a little boring. If you find that it's hard to see what I'm doing on the board or anything like that, please just feel free to leave a comment. I'm more than happy to make another video sort of explaining these things if it's not entirely clear from this one. I just figured since I already have a video of me doing this lesson, I may as well just post that. And remember, follow me on Instagram at @WhatTheHectagon for updates. This video, I'm going to put an update up with probably a picture of me from those 3 years ago making this video. So I hope this is enjoyable. I don't have anything prepared, which is why I'm posting this. But again, if it's not up to snuff, I'm more than happy to remake this lesson, because this is sort of a lesson I wanted to make anyway, but I figured it's already out there. So here it is. Hello students, today we're going to be learning about exponentials and logarithms. I'm assuming that you already have your requisite knowledge on limits and derivatives to start with, since that's what you would need to get to this part of a calculus class anyway. So let's get this presentation started. Okay, so the exponential function, the idea of that is that you have a fixed base a. For now we're going to consider a to be greater than 0, just to simplify things a little bit. But a is a fixed number, and what's varying is the x in the exponent. That's not why it's called that, I promise. So the exponential function follows two very basic and intuitive axiomatic rules. Axiomatic just means they are declared truths, but they are quite intuitive, and I'll explain it to you if I'll have my cameraman turn slightly over here. So if you look at the first rule, it says that a to the x times a to the y is equal to a to the x plus y. And this is intuitive, because if we look at something like x squared times x cubed, this is no different from x times x, which is x squared, times the quantity x times x times x, which is x to the fifth. And because multiplication is associative, the parentheses can go away. And so this is exactly the same as x times itself 5 times, which is equal to x to the fifth, which lo and behold is x to the 2 plus 3. And so we have followed the rule perfectly. The second rule, The second rule is like a double exponential rule. So we have a to the x to the power of y, and we say that this is equal to the quantity a to the x times y. And so I'll use x squared again, and we're cubing that. And so this is the same as x times x times x times x times x times x. It's x squared cubed. Again, multiplication is associative. We have 6 x's. This is the same as x to the 6th, which is 3 times 2, just as the rule says. So even though they're declared truths about the way exponentials work, they are quite intuitive, and they're easy to remember. And so exponentials also have the following properties, which you can derive from the above axioms, and you should be familiar with them, that a to the first power is itself, because exponentials, when you first learn about them, mean repeated multiplication, so if there's just one, then it's itself. By definition, a to the 0 is 1. Also, by definition, a to the minus 1 is 1 over a. In fact, you can derive this fact from this fact in using this rule, because a to the 1 times a to the negative 1 is a to the 1 minus 1, which is 0, and that's the same thing as saying a divided by a. So it should be 1, and that agrees with our intuitions. a squared, a times a, that's pretty easy. A to the 1/2 is the square root of a, etc. So these are pretty nice rules that you're aware of. Okay, so let's take a look at the derivatives of an exponential function. So we understand the basic properties of how they work, so we could try to do calculus with it. Let's try to take derivatives. And we do this, we start with the basic difference quotient that you're all familiar with. You take the change in y divided by the change in x and let that change go to 0 so that we end up with a ratio in the limit that we see as the derivative of a function. And we replace f of x plus h and f of x with a to the x plus h minus a to the x, all over h still. And using the previous rule of the sum of the exponents is equal to the product of the two exponents, we break up a to the x plus h into a to the x times a to the h, which is a perfectly consistent move with our axioms. And then what we're going to do is we're going to factor out that a to the x, because as you can see, there's a common factor there. And now look, this limit is wholly dependent on h. And so a to the x is not affected by this limit, and so we can factor it right out. It's kind of like the derivative of a constant times a function. That's the same as the constant times the derivative of the function, which is exactly what this is. It kind of is, in a sense. But now we're left with a to the x times this peculiar looking limit here. The limit as h goes to 0 of a to the h minus 1 all over h. As you can see, there's no x in this anymore. And all that's happening is these h's are going to 0. So this doesn't evaluate to a function of x of any kind. This is just a number. This just comes out to a constant. And so from now on, we're going to take this limit, the limit as h goes to 0 of a to the h minus 1 over h, to be this function of called h of a. Because as you can see, h just goes to 0, so the only thing that varies that could change the value of this is the value of a. But we don't actually know that it changes it. We don't know anything about it yet. We just know that we can use our logic to deduce that this must just be a number. And so we showed that the derivative of a to the x is simply a scaled version of itself. It's just a constant times the original function. It's either increased or decreased. It could be 1. In fact, we'll see something about that later. So let's observe the case when a equals 2. We see that the derivative, given the rule that a to the 0 is always 1, 2 to the 0 should also be 1. So we see that when we take 2 to the x, so a is equal to 2, we have 2 to the x. At 0, it should be 1. And so if we take the, just turn over here for real quick, so if we take the derivative of 2 to the x, we have, based on what we derived, that we should have h of 2 times 2 to the x. And then we're going to plug in 0 for x, because we're looking here. And so this is going to be 1. 2 to the 0 is going to be 1, so that's going to go away. So the derivative of 2 to the x, evaluated at x equals 0, is just h of 2. And so that's a constant. And as we can see, this is just a straight line. So the slope of this line has to be h of 2. We don't know what it is yet, but we know that that's the number of the slope. And so we understand that we can determine this value. We can only determine this value, actually, when it comes to exponents that we don't know, because we know that it's always going to be 1 at 0, no matter what a is. And so we don't yet, as I said, we don't yet know what h2 is, but later we're going to consider a number e that will allow h of e to be 1. So we're just going to define it that way, and eventually we'll demonstrate that it's actually a thing. But let's take a second to observe that this function 2 to the x, I have a set equal to 2. We have the function f of x equals a to the x, and I set a equal to 2. And so just to show that you are definitely familiar with this, at 0 it is 1. At 1 the value is 2, because 2 to the 1 is itself. At 2 the value is 4, because 2 squared is 4. At negative 1 the value is 1/2, because 2 to the negative 1 is 1 over 2, which is 1/2. So it's all pretty familiar. It's nothing that you're not used to. So we're going to move on to the next slide now. And so we're done with the exponential section. Now we're going into e and the logarithm. And so we're going to define the number e such that the derivative of e to the x, so e is just, we're letting a equal this number e. So we're going to take the derivative of e to the x, and that is, as with other a's, it's h of e times e to the x. But we defined e so that this is 1. So we should just get e to the x. And so we get this, I say remarkable in the slide, but we haven't even proven that e is real yet, so let's not get ahead of ourselves. But we have this property, the derivative of e to the x is itself, and that's going to come in very handy. So we have the exponential with base e is its own derivative, and later on we will prove its existence. And like squares and square roots, which are inverses of each other, we can define the inverse of the exponential function, and we'll call it the logarithm. And so it has this property, like every inverse. If we have y equals a to the x, then we can say that log base a of y is equal to x. They simply undo each other. So if I was to apply, the reason it's base a here is because this is base a. So if we take the log base a of both sides, we should get x, the log base a will cancel out with the a to the x and give us just x. And because y is on its own, we just end up with the log base a of y. They're simply inverses of each other. It's like squaring a number and then square rooting it, or adding one and then subtracting one. You get right back to the original number. And in general, we have two special cases where a equals 10 and a equals e, that we have different notation. In academic high school environments, log base 10 of x is generally just written as log x, just for convention's sake. And log base e of x is written this way, ln of x, known as the natural log, and you'll see why it's the natural one. You'll see why it's really the only candidate for the natural logarithm. It's called ln because I think that's just more aesthetically pleasing than nl, but I'm not arguing with it. Given that these are inverses, we have this property that if we have e to the natural log of x, that is equal to the natural log of e to the x, which is equal to x, simply because they're inverses, so they undo each other. Just imagine x squared and then square rooted. It just gets you back to x, right? That's all it does. And so these simply undo each other. That's it. There's no magic. From now on, I'm going to be using e and natural log for convenience, but most of these rules that I'll be showing deal with any base in general. But e and natural log are simply easier to work with. And so now we're going to take a hard look at the natural logarithm. It is the inverse of the exponential with base e, which means geometrically that it is simply the same function reflected over the y equals x line, because all we're doing is switching the x's and the y's. It's the inverse, so it undoes it. And so given that we've defined e such that h of e equals 1, we see that f of 0 on e to the x is equal to 1, as it should be. But if we just look back over at the board real quick for a sec, if we take the derivative, this marker's losing it. If we take the derivative of e to the x, we see that this, and we evaluated at x equals 0, right? We evaluated at x equals 0. We know that the derivative of e to the x is itself. And so, if I plug in 0, this is equal to 1. So the slope at 0 of e to the x is 1, which is actually I mean, it should be, because e to the x is its own derivative. Since it outputs 1 there, like every exponential function, its derivative should be 1 as well. And we would expect that every output is also equal to the slope of the function at that point, but since we don't actually know what e is yet, I can't determine that, but we will get to it. It's kind of a roundabout way of demonstrating why this stuff is true. So, yeah, I just said all that. Likewise, if we look at g of x, which I've made natural log of x, we have that ln of 1 is 0, which makes sense because e to the 0 is 1, we'd expect that the inverse, natural log of 1, to be 0. It just flips the x's and the y's, as we said before. And its slope is also 1, right there. We can, and we'll show that that has to be the case later. We should also note that because of this inverse, because, if we come back over the board real quick, we know that e to the 1, like anything to the 1 power, is itself, right? So if we take the natural log, and we also know that this is true because they are inverses, that this is just equal to x, right? And so if we take the natural log of e to the 1, which is the same as just the natural log of e, this is 1. This is 1. So the natural log of e is 1, which makes sense. Just like the log base 2 of 2 is 1. It is its own, it's itself. So it has to, they are inverses of each other, so they have to cancel. Okay, now we understand that. Rules for logarithms and evaluating the derivative of the exponential. And so now we have, for logarithms, we have the following rules. These are usually dictated to you in high school class and never explained. High school math class and never explained, but I'm about to prove them to you. So let's turn this over here. And so we're going to define, well, first I should probably explain to you what it is, sorry. So we have that the natural log, and remember, I want to stress that these rules apply to logs of any base. I'm using natural log purely for convenience. If you take the natural log of a product of numbers, it can be written as the sum of the natural log of both of those numbers. Okay, and I'm going to prove that to you using the axiomatic rules that we had for exponentials before. So, let's define a to equal e to the x, which implies, with log rules, that the natural log of a is equal to x, right? We're just taking the natural log of both sides. This becomes natural log of a, this just becomes x. And we're defining b as e to the y, which also implies that the natural log of b is equal to y for the same reasons. So let's look at this. So let's look at the natural log of a times b, and given what we've defined them to be, we can replace them. So this is equal to the natural log of e to the x times e to the y. And if you recall the axiom we had about exponents, I can write this as a single exponent with the sum of the powers. So this can be written as the natural log of e to the x plus y, okay? And since natural log and e cancel, this evaluates to just x plus y. Because if you recall, given the rule that we had before, the natural log of e to the x is just x. So whatever I plug in for x here just ends up out here. And we have x plus y, so this evaluates to just x plus y. And if we look back at our definitions, we see that x is the natural log of a and y is the natural log of b. And so this evaluates to just the natural log of a plus the natural log of b, which is exactly what we set out to prove. And now we have our proof. The natural log of a times b is equal to the natural log of a plus the natural log of b. And now, using that fact, I will prove the second rule. So the second rule states that if we have the natural log of some number a to a power b, this is equal to b times the natural log of a. And this can be proven using the same rule that we just proved before. So let's take a look. So if we have the natural log of a to the b, this is equal to the natural log of a times itself, b times, right? It's just repeated multiplication. It's just a times itself, b times. And given that we have this rule, that we can split it up into sums, I can write this as a sum of the natural logs of a. So just again, just writing the natural, I don't need parentheses, the natural log of a bunch of times, and we see that because it's a multiplied by itself b times, we can write this as a sum that is b terms long. And because it is b, it's the natural log of a added to itself b times, this is simply b times the natural log of a. And so we have demonstrated it, the rule, they are equal, they are equivalent. And so now we can use those facts to prove the derivative of the exponential. And so let's do it. So we have a to the x, the derivative, a to the x prime, which is another notation for derivatives. We can rewrite a to the x as e to the natural log of a to the x, because remember, e, the exponential, and the natural log will simply cancel and give us a to the x again. So there's no confusion there. And given the rule we just proved, this rule right here, we can rewrite the natural log of a to the x as x times the natural log of a. I hope that's clear. You can just move that down. That's what we just proved. And now, again, assuming you had the requisite knowledge, we're going to do the chain rule. So we're going to take the derivative of e to the x log a with respect to x log a, and then multiply it with the derivative of x log a with respect to x. Now, what we learned before is that the derivative of e to the x is itself. So this will evaluate just to e to the x log a again. It is the derivative of itself. But then we need to take the derivative of the x log a with respect to x. Now remember, this looks like a jumble of stuff, and it looks a little confusing, but the natural logarithm of a is just a number. We can see that in the graph that we showed before. If you plug in an a, you get a value. It's defined for every x positive. And so if a is a positive number, this is just a number, and the derivative of x times a constant is just the constant. So this is just a constant. So we end up with it, and the constant is the natural log of a. So we end up with e to the x log a times log a. And if you look back, we have that e to the x log a is equal to a to the x. And so we can just simply replace this with a to the x. And we see that the derivative of a to the x is a to the x times the natural log of a. And so we have proven that that mysterious h of a that we had before, that weird limit, is actually just the natural log of a. And so that's kind of a cool connecting of the dots there, but the circle is not yet complete because we do not have e yet. So we've solved the problem of the exponential though. We've shown that h of a is equal to ln of a, and short of proving that e exists and is unique, we have demonstrated that e to the x must be its own derivative. So now we just need to get to set off on proving that e is actually a thing. Oh, but I did want to make one note on the awesomeness of the natural logarithm. So it's clear that it must be the natural one, because if we look at the derivative of more familiar numbers like 10 and 2, which we use a lot more, because you don't even know what e is yet, so you don't know if you've used it before. It could be a regular number, but we don't know. So if we take the derivative of 2 to the x, we end up with 2 to the x times this pesky constant, natural log of 2, that we haven't defined yet. If we take the derivative of 10 to the x, we get 10 to the x times the natural log of 10, another pesky constant. But if you take e to the x, the derivative of e to the x, you just get e to the x. And so it's a much more elegant thing than just to have these kind of, what's the word, cumbersome derivatives, comparatively speaking. And since e to the x is its own derivative, you can derive it over and over and over again. Differentiate it over and over and over again, or integrate it over and over and over again, and you will still end up with e to the x. So it's kind of a nice little thing. And we will see that it is in fact a number that is unique and exists. And so we're going to prove that it is the case here, but we first need to demonstrate one more fact before we can get on to proving what e is. We need to show what the derivative of the natural log of x is. And this one's kind of a surprise. I'm sure the first person to discover this probably didn't see it coming, but it's quite nice. So let's do it. I'm also assuming that you have done implicit differentiation, because that's something that will come before this as well. And so implicit differentiation is simply taking derivatives before you've necessarily solved for y, or actually unsolving for y on purpose to make the problem easier, and you'll see why that is in this case. So we're going to look at y equals the natural log of x, and we're going to exponentiate both sides. So we have e to the y equals e to the natural log of x equals x. And the reason, so we have e to the y here, so we've just raised y, e to the y power, and then raising e to the natural log of x power just gives us x, because remember they cancel. And so we have that e to the y equals x. There's nothing special here, I just exponentiated both sides. And this implies that the derivative of e to the y is equal to the derivative of x, right? If we do the same thing to both sides, we have an equation. So what we're going to do is, we have to do the chain rule again, first of all, because y is a function of x. But the derivative of e to the y with respect to y is just e to the y. But then we need to multiply by the derivative of y, which is y prime. And the derivative of x with respect to x is just 1. And so we have this little equation, e to the y times y prime equals 1. So we can divide both sides by e to the y, and we end up with y prime. And remember, y prime is just the derivative of the natural log of x, because y is the natural log of x. So we're trying to find the derivative of that. If we divide both sides by e to the y, we have that y prime is equal to 1 over e to the y. And what's e to the y? E to the y is x, right? We have this equation here. E to the y is x. So the derivative of the natural log is 1 over x. Kind of an astounding little result there. I'm sure, like I said, the person who discovered that probably didn't see that coming. We also have another cool thing called the logarithmic derivative, where you take the derivative of the logarithm of a function. And so we have to take into account the chain rule. So we take the derivative of the logarithm of the function with respect to that function. So this is just going to turn out to be 1 over that function, right? So we have the derivative of the natural log of x is 1 over x. If I just plug in f of x there, I'm going to put f of x here, right? That's easy. It's just plugging in. But then we also have to take the derivative of f of x with respect to x, which is f prime of x, because we don't actually know what f of x is. It's a general statement. And so we end up with the f prime of x divided by f of x. So the derivative of the natural log of a function is equal to the derivative of the function divided by the function. So that's an interesting little thing. And like I said, that's called the logarithmic derivative of f of x. Okay, now to actually proving the existence of the number e. We're going to do that by evaluating this limit. The limit as n goes to infinity of the quantity 1 plus 1 over n all to the power n. So this entire term is the limit. Is being limited by n going to infinity. Okay, and we're going to evaluate it using the properties of the natural log of x. So what we're going to do is, we're going to do something called taking the log of the limit. Now, what that is exactly what it sounds like. I'm taking the natural logarithm of this limit. An interesting fact is, since n is always positive, it's going to positive infinity, so n is just going to be increasingly positive. The natural log of x is continuous and differentiable on every x positive, and since this is always going to be a positive number, it's also, and varies continuously as n goes to infinity, it is also going to be continuous and differentiable in positive x. So in fact, you probably need to do a little bit of analysis to totally grasp that, but by that fact, the log of the limit is the same as the limit of the log, because they're interchangeable, they're continuous and differentiable on all points of n positive. So you can switch them like that. Maybe do a little review of analysis, and you'll probably get a better grip of why that is. So, because we now have the limit of the logarithm of this, and we're following the log power rule before, we can bring this power of n down in front of the log, if you recall that one of the log rules. And so now we have the limit as n goes to infinity of n times the natural logarithm of 1 plus n, 1 over n. And so what we're going to do now is we're going to do a clever little substitution. We're going to let n equal the quantity 1 over h, okay? And so this is going to change a few things. In the limit, it says n goes to infinity, but if n goes to infinity, then that must mean h has to go to 0, right? Because as you divide 1 by smaller and smaller numbers, n will shoot up. But h then has to go to 0 for this to go to infinity. So now, instead of n going to infinity, we have h going to 0. And if n is 1 over h, then 1 over n has to be h, right? We reciprocate both sides, so 1 over n is h. So we're replacing the 1 over n here with h. And this n is now 1 over h, so we can just put the h in the denominator. And now we're going to do one cool little trick. We're going to subtract 0, which won't change the problem because it's going to remain the same value. If we subtract 0, then we won't have an issue. And that, in the form we're going to do it is we're going to call it the natural log of 1. And if you recall, to the other function, it crosses the x-axis at x equals 1 because it's a reflection of e to the x. E to the 0 is 1, so the natural log of 1 has to be 0. And so this is 0. But look at this. What does this look like? This looks like a very familiar form. This is the difference quotient. This is evaluating the derivative of the natural log of x at the point 1. That's all this is. This is clearly f of x plus h minus f of x all over h, where x is equal to 1. And so since we proved before that the derivative of the natural log of x is 1 over x, we can say that since this is being evaluated at 1, this limit is equal to 1 over 1. Because if it was just x here, this would be 1 over x, but we're evaluating it at 1, so this is 1. So 1 over 1 is equal to 1, which means the log of this limit is equal to 1. And so now we're going to undo the logarithm by exponentiating both sides of this equation. So we now have that the log of this limit is equal to 1. We're okay with that, I'm sure. So now I'm going to raise both sides of this equation. They're now going to be e to both sides. So we raise this side to e. E to this power, and because it's e to a natural logarithm, since it's e to a natural logarithm of something, the e and the natural log cancel, and we just end up with that something. So now we're just left with the limit. But remember, the right side of the equation is now e to the 1. And so e to the 1 is just e. And so this limit is exactly e. And so if you pick n sufficiently large, say 1,000, and do 1 plus 1 over 1,000 and raise that to the 1,000th power, you will get a very close approximation for what this number is. And as it turns out, and I will not be proving this, that e is irrational. And it is approximately 2.71828. And so it's quite a nice number for the usages that it has. But but it's not a very nice number numerically. And so given that, we have one more section to go through. And so here's a couple other properties that are quite nice. You can do this thing called change of base, which we did not need in proving this, but it can be useful for other problem solving, and I will prove it on the board. We have this fact. If you have a logarithm of base a of b, you can rewrite it as a logarithm of base c of b divided by logarithm of base c of a for any a, b, c. So if you have log base a of b, you pick a new base c and take that logarithm of b and divide it by the log of a, and I'll prove it over here. So if we let x equal log base a of b and exponentiate both sides in base a, we end up with a to the x equals a to the log base a of b. And since the base of the exponent and the base of the log are the same, they cancel each other, and this is just b, right? This is just b. So this equals b. And now what we're going to do is we're going to take the log base c, where c is some other number, of both sides. And so we end up with log base c of a to the x equals log base c of b. Now remember your power rule. I can bring this exponent down in front from the power rule we proved before. And so this is x log c of a equals log base c of b. Now we can divide both sides by log base c of a. So I'll just cross it out there and I'll write it down here. And we have that x is equal to this over that. And remember, x is log of a, is log base a of b, and now we've proven that it is the rule that we just said before. So we have that rule now. We also have log properties. We can also use them to prove really annoying derivatives like this one, where we have y equals x to the x. So we have not only a moving exponent, but also a moving base. And so what we're going to do is we're going to take the natural logarithm of both sides, and then using the power rule for the log, I'm going to bring the x down in front. So we have the natural log of y is equal to x times the natural log of x. And now if you recall, we had that logarithmic derivative property, where if we took the derivative of a logarithm of a function, it's equal to the derivative of the function divided by the function. So if we take the derivative of the natural log of y, we have that it is the derivative of y over y. And remember, y is x to the x, so we can just factor that. We can just fill that in right there. So we have y prime over x to the x. And this is equal to the derivative of x log x, and we use the power rule, so we end up with x prime times log x plus x times log x prime. X prime with respect to x is just 1, because it's x. That stays there, so we end up with x, so we end up with 1 times log x, which is just log x. And then the derivative of the natural log of x is 1 over x, and x divided by x is 1, and so this evaluates to natural log of x plus 1. Multiply through by x over x to the x, and we see that y prime is equal to x to the x times the quantity, natural log of x plus 1. And so you can evaluate that derivative using logarithms. Otherwise, you could use exponentials and logarithms at the same time, which is a different way of doing it, but it's about the same amount of work. And without those two tools, I'm not aware of any other way to actually solve that derivative. We can even use logarithmic differentiation to reaffirm our original goal of differentiating the exponent. And so we take y equals a to the x, we take the natural logarithm of both sides. This simplifies to a log x because of the power rule. We redo the logarithmic differentiation and replace y with what we defined it to be, a to the x. So we have y prime over a to the x, and that's equal to, there's a typo, I think. No, I'm sorry, no, I've taken the derivative. So this is just the derivative of x log a, right? Because log a is the constant, and so we take the derivative and that's what it is. Multiply through by a to the x, and we have our original goal that we proved before. Y prime is equal to a to the x times natural log of a. So we only have one more slide, and that is practice problems. And so, after having watched this lecture, you should try these derivatives. They aren't difficult. Derivative of 3 to the x, derivative of natural log of e to the x, and all this is just a combination of chain rule and sum of the derivatives is the derivatives of the sum, so it's not a difficult problem. And as a little extra, I want you to try evaluating these general derivatives. What's the derivative of the log base x of a? So x is varying, a is constant. So you may have to take into account this rule. And this one you don't. I mean, you do to rearrange it, but you don't really have to do much math after that. This one's slightly different, so the x is varying here, and the base is constant at base a. So this is just a general derivative of any log. So if you were to plug in e, you should expect, if once you evaluate this derivative and you plug in e for a, you should expect it to simplify to 1 over x. If it doesn't simplify to that, you've done it wrong. And now, as a bonus, last thing I'll ask you to do is I want you to prove the well-known power rule that the derivative of x to the n is equal to n times x to the n minus 1 using the rules for exponentials, not using binomial theorem or any of that, using exponentials. And in fact, using exponentials because they're continuous, and you also need logarithms, but using both of those because they're continuous, it actually generalizes this fact to all real numbers, and in fact all complex numbers. When in fact proving this just using binomial theorem only proves it for positive integers, and so that's actually quite nice that it does that. So thank you very much.